Fine. Everything started here. So basically, Alexi is one of our colleagues working in Sydney, and when I was in Sydney, basically on Slack sent me this cryptic message. It's like, oh, I don't know, send more money. I said, what are you talking about? And then he told me, oh, hold on a second. This is a crypto-arithmetic thing. So basically, every letter corresponds a digit. Have you ever seen this kind of little games, you know, from the 70s, 60s? And the leading letters cannot be zero. So these are the only two rules. And the numbers you're forming with the digits, when you sum them, you get, you know, a number that corresponds to the right letters. I'm Italian, and there's two Italians here accidentally tonight. This is very famous in Italy, right? And there's one of these games, it's very similar, the same thing. So I said, oh, hold on a sec. I know, I spent like, when I was a kid, I spent a lot of time doing this thing. I'm very good at that. So I start with pencil and paper, and I say, hold on a sec, what is that? Of course it's 1. Because when you sum, whatever you sum in here, that will be 1. So I wrote M1, and I sent a reply back on Slack, M equal 1. And then again, what is this? This must be 8 and 9, but this must be 0. Whatever you do here, this must be 0, because it was the same one as, you know, it was 0. So the thing is, I started typing on Slack, and it was telling me, hold on a sec. I wrote you that because he was reading a series of blog posts by Bartosz. I don't know if you guys know that guy. I mean, this is Ekmet. He wrote basically half of the code base on Hackage, basically. But this is Bartosz, and he's a very nice guy in person, but online he's writing a lot of tutorial for C++ developers on how to be functional in C++. So he's bringing all those concepts to C++ developer because he's a very strong C++ developer. So Alexi was talking about, tonight we're going to talk about monads. So basically he's even telling the C++ developers how to use monads in C++. So he was talking about a series of blog posts made by Bartosz and about that simple problem. Like it's a crypto-arithmetic problem or verbal math, whatever it's called. Anyway. So tonight we're going to try to use that example to see how he solved that problem, how I would solve that problem, and how I found a paper on solving that problem in a very good way. So this is more or less the agenda for tonight. And of course, there will be more. Okay? Let's start, you know, to touch the water to understand what's going on with the naive implementation. How big is the search space? So if we try, if we try all the possible candidates, we're talking about 2 million. Okay? I mean, 2018, it's super small, right? 2 million is nothing. But, you know, it's a nice thing. So we are an imperative programmer, a bunch of programmers. So what we're going to do, we can make like 8 nested loops, 1 for each letter, and then we set the constraints, and then we find the solution, right? That's one way to do it. That's the brute force way to do it. We generate everything, we test the constraints, and we get a solution. Fine. This is the same thing in Scala, okay? So because I'm using Scala tonight, basically the syntax is very clear. You have the if here instead of the and. So in other words, we search the candidate solutions, and then we check if the constraints are satisfied. And I'm trying to be fancy here to stay in a slide, but all I'm doing, I'm creating the numbers, I'm summing them, and I'm checking if, you know, the sum works. Okay, one thing about that, there's a lot of code here and a lot of repetition. Okay, this is super ugly. It's so ugly that when I did this slide and I tried to run the code, there was a bug. Because when you do copy and paste all the time, it's so easy to make, you know, to create bugs. Okay, this is the brute force. We all know how to do this, right, in an imperative way. Fine. So this is not what the blog post was talking about. Bartosz is very good, but he's a quantum mechanic physics guy, and he talks in a very correct and formal way. Tonight, I'm not going to talk in a very correct and formal way. Actually, I prepare a bunch of slides on the side. So tonight, I'm going to try to be a little bit inaccurate in order to, you know, save a lot of time on explaining things. So please do not hold on what I'm going to say tonight. okay? Jimmy and the multiverse. Shit. Okay, first of all, I did this presentation in Italy, like the first part, and today I was, what the hell? I'm Italian. No, the thing is, I forget to convert all the slides. Fine. So Jimmy and the multiverse, you know what I'm talking about. This is Jimmy, okay? He's a bingo caller. So he picks number out of this jar, and when somebody makes bingo, he screams bingo, okay? Bingo caller. So we have the jar. In our case, our jar could have like these 9 digits, okay? And what Jimmy is doing is picking up a ball, but until he sees the number on the ball, we do not know what is the number, okay? So what I'm trying to do here is that we don't know which number he picked up until we watch it, okay? So if it's 0, then we know that the leftovers are these ones, okay? Stay with me because I'm bringing Schrödinger, okay? I have a good news and a bad news. So basically, we are in Schrödinger right now. So until we check the number, we don't know which number we have in our hand. That means that we could consider the first pick a spawn of 10 universes, okay? This is exactly the kind of algorithm we're trying to do tonight. So if we are in this one instead, when it's 1, these are the leftovers. So when we get into the universe and we pick for E instead of the S, so we pick the second ball with the number, we spawn how many universes? 9. No, 8. No, 9. 3, 3, 6, 9. Sorry. Okay? Multi-universe. Super simple. Now, what would make other do? So this is a functional programming in Meetup. We're looking for something, how the functional programmers can actually solve this problem. There are many different kinds of monads. Let's start using the list monad, okay? And, okay, I say list monad on purpose. So when I say monad tonight, all I mean is just a computation and a way to bind computation together to have a bigger computation composed by small computation. So at the end of the day, I'm making computation and try to make it in a very explicit way. I understand I was not very clear. So let's look at an example. So this is Scala. Every time there is a 4 and a yield, this is not like a 4 like a C++ or C4. This is called for comprehension. In Haskell, it's the same as do notation. I know there's somebody in Haskell, Haskell a little bit. So this is the do notation. So this is basically a kind of a bind of flat map in Scala. Okay? Okay. So in other words, every time you see this, and we try to see so first of all, we need to look at the type. We need to follow the type. So quick question for you. What is the type of L? Every time we look at this, the type is always the type of the monad. So in this case, the monad is list. The type of L must be list. Okay. Now, this is the parameter. So it's parameterized list, of course. What is this parameter? The parameter is always what we yield in. So here we have a list of integers, but at the end, we're going to map on a map. So a lowercase map on a map. Therefore, the type of this is this type. So in this case, it's a character to a. So a character to an integer. Okay, a map from a character to an integer. Again, the monad is the one of the for comprehension here, so list, and this one is the type of what we map at the end. Okay. But there's a problem. We were trying to spawn universes, but here, look at that. We have all the combinations, right? 1, 1, 1, 2, 2, 1, 2, 2. Actually, what we really want is this universe and this universe. The one where we pick 2 and the one that we pick 1. Okay, so subphase. What we have to do is to get like relief, we need to use an if. But this is not what a functional programmer wants to do, right? So probably list is not the monad we're looking for. It's kind of there because it's branching, but it's branching too much. It's creating a universe that we don't want. Okay, this is hard. So now I'm going to introduce the state monad. Is there anybody not familiar with state monad like at all? 0. Yes. Perfect. Okay. Okay. Perfect. I think the state monad is it's kind of hard to understand the first time, so it's fine. Please interrupt me, ask me questions if you want. But let's not get everything lost. Let's think about the state monad. It's a concatenation of these two lists, like, concatenating, like try to branch everything out. Let's look at the same thing for state. Let's define a function. What is a function? A state transition. The simplest possible way, we have a state, S, and we go to what? To a state and a value. So we have a computation. You pass the current state, you get the future state and a value. This is the simplest way we can define a computation. A stateful computation. And by the way, there is I left every slide, I try to leave links with references. And by the way, if you really are interested in state monad and Scala, there is the book that I'm always showing in Brad, right? I keep showing it. There's a chapter just about the state monad here. It's one of the best ways that I found that a state monad is explained. So, Brad book, it's very nice.
What's the significance of the plus sign?
Plus sign?
Plus A.
That's a very good question. Covariant, contravariant. Because Scala, this is Scala, because Scala has inheritance, you start digging a hole into the covariant, contravariant thing. Like Java, the same thing with Java with generics. Oh, you need to covariant, contravariant, because inheritance. If you do not have inheritance, you wouldn't have a problem, because of subtyping. So in this case, this is the producer. I never remember the way. Anyway, the thing is, you try one way. If it doesn't compile, it's the other. This is one way. Again, I think you just encapsulated Scala programming.
Thank you for saying that. I'm a Scala programmer, and that's what I do.
Exactly. A little bit of inaccuracy saves a great deal of explanation. No, seriously. So we have a computation. We pass one state. We get a future state and a value. Okay. So this is the type of our stateful computation. That's it. If you get this, state monad is just a machine, okay, to make this happen. And that machine in Scala is basically made with a function. So you create a state monad with just that function. That's it. So if you can write a function that get a state and give you back a state at the next state and a value, you're done. Okay? That's the point. It's that simple. So I keep this one here just to remember, okay? Now, let's implement this. What is S and what is A? So what is the state? For us, is the bag full of balls with the numbers, okay? This is the state. I use list. I could use a set, but I can use a set for another reason. By the way, I'm using list. Okay, so S is the list, the bag with balls. So we have a bag, and we have a future bag without the ball, okay? The ball is the number. So what I'm doing, because I'm lazy, I'm just using the tail, so I'm picking up the first ball of the list. Okay? This is the value of the future state, and this is the value, this is the value of the future state, and this is actually the future state, the bag without the ball. All good so far? Now, this is where things could get crazy, okay? Because we're using the state monad. And I'm pretty sure it's very clear to me, but could not be clear the first time you see that. Same thing as the list. We have a for comprehension, and we have this value. Let's follow the type. What is the type of S? State. It is parameterized. What is the value of S and A? It depends. It depends on the function, right? Sure.
I don't understand the syntax. What's
Sure.
A less than dash state? So,
Yes. So it's like the do notation in Haskell. So basically,
just like one with that one.
this one.
Yeah.
So basically, this is called flat map. So
Okay.
or return. And this is where I call Mark to help me out, try to explain a monad without being too complex. So basically, to have a monad, you must have two things. One is the unit and unit function, and the other one is the return or flat map. This is that one, flat map. So I give you the signature. So the signature, you go from A to M of B, right? So you have from MA. Mark, I need your help, right? So you pass these two ones, and then you get M of B. That's the return signature, more or less. Looks like, out of the blue. I didn't prepare that. We should Google it. But all I'm saying is that we can make like 2 hours talk just about this and the unit. I have a slide for that, actually. What is a monad? This is a monad. Okay.
It gets worse.
Now we're talking.
So this one is the moon. So, okay, we should talk about this stuff. So, in other words, okay, let's go.
What is the
Filippo.
diagonal? That's not an arrow. What is
No,
the
this is like, these two are the same. What he's
Oh,
saying
okay.
here is that if
That's standard?
if you apply, no, that's if you apply to T eta is like the identity function, you get T2. Same thing here, T2. And then if you apply, if you apply T eta or eta T, you get to these 2 points. If you apply mu to these 2 points, you go back to the same thing.
Okay.
This is what it says.
Theta.
Say again? Anyway, sorry, no, that was just to confuse you more. No, it's a good question. It's a good question. So what this does, it's basically, when you are in a core comprehension, it should feel like an assignment. So basically, you're opening the monad and getting A from this. Why? Because then you're going to use this somewhere else. In this case here. Sometimes you concatenate monad one to each other, and you don't do that. But this is what it does. So to be inaccurate but kind of clearer, I would see that as a kind of an assignment. Okay? So, in other words, we were looking for the types here. So we need to look at select. Select was from list of int to list of int. Okay, this is a tuple. Okay, so select. So the type of A, this one, will be. Can you see list of int of what? Of character and int, because int was that A. So maybe I need a slide in here in the middle just to explain this better. But these types are coming from this function. Okay? Again, the state is still list.
And so how do you read that left pointing arrow?
This one, I call that flat.
You
In
call that
Scala. Flat. It's the return in Haskell.
Okay.
As I said, probably I will look tonight, I will look, if it's the first time you see like a model in Scala or any language, I will look at that as a kind of an assignment. Kind of an assignment.
I thought that's the point, isn't it?
Yeah, that's the point, to try to feel like an assignment.
Yeah. Oh, sorry. I missed that.
Assignment, right? Can you say that
Yeah,
better? I'm trying.
No,
Yeah.
that makes sense.
If somebody can say that better, please.
Just a Scala syntax question.
Sure.
The parentheses around the state, that's for the types, not the parameters for constructor or anything like that.
Like this one.
No, on the left. Yeah, when you're binding state select to A, that's the type parameter, right? For the types of functions.
Actually, no. That's a very good question. Thank you for asking. So I'm going to answer this question right now. That's a very Scala thing. So basically, this is called a companion object. So basically, we have a state, and we are instantiating this thing. It's basically a static method. So when we call state parentheses, we're going to call this apply. That's super Scala. That's actually Scala itself doing that. I've never seen any other language.
So
You're calling this. So again?
So that's you're passing an actual real pointer to that function to state, and you're okay. So it is a constructor.
It is a constructor, yes. This is the way you make a constructor in Scala.
Okay, so you're, okay. I can, that works.
Thank you. No, seriously, that's actually a very good point. So this is the way Scala works. And here, then we construct a state with that function. That's why all the types then will match. Now, what is the result of this? So we know the type, but what is this? And this is the main point when you start talking about monads that are not list or maybe monad of something slightly more complex like function, like the state monad, okay? The return of this, if you type S, what is S? The only way to do something X is to call eval. S is the computation itself. It does nothing. As we said at the beginning, a monad is just a computation. You need to evaluate something to get something out. That's the main point. Okay? So S is a machine ready to rock and roll. Okay? You just need to give me the cookie to give you out something else. You know? You need something to work on. So it's just the description of a computation. In this case, please create me a map with A and B. But check this out, what's going on here. Because it's a state monad, and believe it or not, the function is actually working with state. We're actually remembering that we pick the 1, and all we have to pick next is 2. Why? Because the function we passed takes the head of the list. Okay? So these crazy people that call themselves functional programmers, what they do, how they deal with state, that's one way to deal with state. Okay? So they're using functions that modify the state in order to modify the state of the list passing through the pipe. Okay? And second thing, this is a computation that we need to evaluate. Now, what's happening when I pass 1, 2, and 3? No, that's not the example. When I pass something else, it works. When I pass 1, 2, and 3, this is list from 1 to 3, and I do this, I get that. Okay? This is the state monad. It's hard to understand.
Can you go back to the previous one?
Sure.
What's like, this has got a different breakdown because it's got this val s colon, all of this right here. Is it, and then you go to the next slide and you don't have that.
That's just the type signature.
Oh, okay.
Oh yeah, that was
Yeah.
the signature. I left there like, what is this?
Yeah, that's what I wanted to know.
Okay.
Does-
When? Yeah.
I'm sorry, I'll
Yeah.
finish your question. I'll be in.
No,
So one
no,
more
I'm good. I just wanted to know what that was.
Why I keep doing this?
Yeah,
Because for me-
why you did this on this one but not on the next one?
Yes, because it's the same type. Why I'm doing this in general, I always follow the type. Every time I have to bang my head against something functional programming complex, the types is the only way to understand. It's like the rocks where I can actually walk. Without the types, I'm lost.
Okay.
I'm seriously, there's no way I can get my head around this.
Yeah, so this is also me not being super familiar with Scala, but is state in does the outer the S is a state? Does that come from the semantics of the core notation, or does that come from the fact that you're finding states that A and B? Is that inferred from the internals?
Sorry, I don't understand the question. So the
Does the inference of state T for S come from the semantics of the for yield
yeah,
construction?
absolutely.
So for yield it's a state. It's not inferred from the internal.
No, hold on a sec. It's inferred. So basically, I can rewrite this with just function call. If I'm doing okay, live programming. What can go wrong? Okay. So let's open IntelliJ. We can actually desugar that, and it would be just a function call of a function. So flat map, and then the inference, like the type system, is doing that for me.
All right.
And make it compile or not. Okay, this is the
Perfect text size.
yeah.
Yeah, we can read it. Oh my god, so we have to do view presentation mode, right? Add the presentation mode.
Yeah.
There you go.
I tell you what, I'm gonna.
I think there's a -5.
Yeah, give me 1 second. So I'm gonna show you. Oh no, that's another solution. Spoiler, no.
It's okay, no one can read it.
I can read some of it.
Here we go. Give me 1 sec. So
Use the magnifier bulb.
Yeah.
okay, I give you this. Oh, you're right. There's this one.
So you can change the font size and the intensity.
Well, the thing is, I tried already. It takes time. Okay, that's much better, right?
Yeah.
So let's say this, whatever state. Actually, it's the same one as before, doing something slightly different. I can do this because IntelliJ is IntelliJ. This sugar.
Ooh, that's cool.
One line,
Okay.
perfect.
And I'm so fast I didn't see it. What'd you do?
I just press a magic button, and now we have state. I will have state, flat map, and then a function of state, flat map, and then a function of state, flat map, and then at the end of the map, at the map.
Okay.
This is JavaScript guys there. The few JavaScript guys there. So this is like the Christmas tree you have in JavaScript, you know?
It's a,
How it's called?
it's like a macro callback.
Yeah, callback carousel. Anyway, you get like deep.
Yeah.
But it linearized that. Yeah.
Okay.
So if I were to purify
But it is pulling up the type. I just wasn't sure if the for construct is defined in terms of that or if it.
Man, very good question. Thank you very much. Yeah.
If you do the same list, it's still an element cube. It just makes it look like it's better.
Right.
Okay. S is just a computation that we evaluate something and we get something out. But this is not what we're looking for. What is this? This is just one universe. So we're not spawning to multi-universe. We just get the first one, the second one, the third one, and that's it. So we have one possible universe. We're not spawning universes, okay? See? It's going that first. So if you think about all the possible universes, we are going that first.
So you random.
Sorry, go back.
No, I like this. Okay.
That pipe, right arrow,
This one?
is that one symbol or two?
Which one, sorry?
The
the
pipe.
thing that's making the list.
This one?
Yeah, yeah.
Oh, I'll show you what this is. This is
Is
super
that,
simple.
no,
It's
is that one
Scala
operator or is it two?
Z. It's this.
Scala Z likes to be weird.
Scala Z, sorry, we're in the US. Scala Z is basically this. It's a shorthand to make a list.
Okay.
It's just sorcery, you know, for one to three. Because unfortunately, Scala, simple Scala, if you do this, you don't get a list. You get a range.
Great.
So you should create a list from a range, and that's why there is this
Well, how
shorthand.
do you read that, though?
This one, list from 1
Yeah,
to
those
3.
three characters, how do you read it?
That's another problem that everybody has, that Scala Z is basically very hard to understand. So what you have to do, you have to go into the definition of that, and it's like, oh, I understand now what it means. But it's cryptic because it's using symbols everywhere. So that's a common.
I just find that all these functional language people gloss over
And I
how
tell you one thing,
symbols are pronounced.
you're lucky. There's no Unicode version of that. Otherwise, you have a Unicode symbol that you need to know.
Oh, I'm sure there's
Like
a
Google.
math symbol that looks like that.
Right?
Pick up slowly.
There's
I think there is a Unicode symbol for that.
Say?
Don't tell them that.
There is a Unicode symbol?
Oh, yeah, that's a common math symbol.
No, I think it's in the like arrows and frames section.
It's a weird section.
Then it's Unicode for the arrow by itself.
Sorry?
There's Unicode character for the arrow by itself. Like,
Yeah.
yeah.
Oh,
Yeah.
It's a symbol, just
And it's allows you to use that.
yes.
Well, and
yes.
you can certainly just stick something on the side of the vertical bar.
Anyway.
Yeah.
Anyway.
I want to show you the chicken. We have to be, because we cannot give up. So with state, we go that first with one universe only, so we can spawn multiverse. With list, we spawn way too many multiverses that they don't even exist. What can we do? Monad transformer. So state T is a monad transformer in a, what is that? Transformer is something mathematical, something functional? What is that? I don't even know where it comes from. But anyway, the point is, with monad transformer, you can actually match together two monads. In this scenario, we would like to try state and list. Okay, let's try this out. So this is the way Bartosz in that series of blog posts was explaining. Yeah, let's smash them together. Let's get the power of, you guys know the record of Z, equals Z. You know it, right?
A child did.
Yes.
I think that's what EMS maybe.
So that's the thing. Monad transformers are very scary as well. Powerful, but scary. Scary. That's it. So how are we going to change our select, the function that goes from one state to another one? We look for the type. We follow the type. State type, F is functor, in this case the monad. So basically F is list, S still a list of ints, okay, list of integer, and A is the integer itself that we pick from the back. Okay? So this is the signature of select. We pass a list of our things, and this is the next state. So initial state, next state, value out. But we have a list of them. See the difference? Now that we're using F as the list monad, we have a list. So the state is spawning states, not just one state. Can you see that? So all I have to do is just implement this. I know this is like me writing Scala. So it's very simple. All it does is for every ball inside the bag, is creating a bag without that ball and the ball itself. We are spawning the universe. So we are having from one bag with 10 numbers, we're going to have 10 bags with one number out, and 9 numbers in all the universes. In other words, this. Okay? If you look at the function, this is what it does. It's just one line, okay? So far so good? Same thing. Flat map, flat map, flat map, flat map. Now, I have my stateful computation. What would be the result of that? I don't know if that's working remote. Oh yeah. And that's me like, oh my god, it's working. Yes, we spawned the exact things we were expecting, okay? There's no if, okay? No if. We are spawning the universe we were expecting. Honestly, when I read that, that was pretty cool. That was pretty cool because that stateful computation with that select, it's so incredible that when you use the same thing in this, for comprehension, we get a different number, okay? So for every flat map call, here, we get a different number. So this thing is chaining the states and is giving me a different number all the time without any if. For me, honestly, when I saw that last year, that blew my mind. Okay? And this is just using a monad, actually 2 monads. Okay? Let's solve this puzzle. I know, probably takes a little time, but trust me, with just that thing, you can do this, and it works. Let's solve the problem. That's just coding, okay? We have to apply those two ifs. I made a presentation, if you're interested about Monad Plus, that will take half an hour just about Monad Plus, so we'll not talk about Monad Plus tonight. If you're interested, I made this presentation. Sometimes all about that. So this is the final solution. That's it, done. We're going to yield the answer. That's it. This is the blog post series. This is the way Bartosz, in that blog post series, solved this problem. It is elegant. I would never use it for like real thing. For real thing. But this is monad transformer. I mean, this is a function program Meetup. We should show monads, okay? This is probably the way I would solve it, okay? I create all the combinations. I create all the permutations, 40,000 permutations. I will have my 2 million things to test, and I will test it, okay? Done. I have my maps, I test it, and I give you the solution. Done. super fast. It works. You know, super simple. That's one way to do it. Now, from a computational point of view, what is the difference between, from an algorithmic point of view, what is the difference between this one and the other? Nothing. They are all depth first search. Even if we spawn universes, we just check, we swipe all the universe from left to right, one after the other one. Either way. So these are all depth first searches.
So go back to your explanation, the previous slide.
Yep.
So you're using combinations and permutations, or is there some library?
Oh, this is a scala itself. So basically, this is a range and create a combination. So this is a list, I think, was a sequence-like.
So it's creating
Think about
a
list model.
combination entity that's got all 45?
These are 45 different ones. So these are, okay, that's a very good question because it will be helpful later.
It's representing all the combinations. It's iterable.
Okay. It is iterable. Yeah. This is a list. This monad is a list monad. This for comprehension is over a list monad. So why it's 45? Because we have 10 numbers. We need to drop 2 of them. Okay. So we have 8 of them. If you try all the combination of these 2 ones, so basically it's 45 because it's how we're gonna don't use those 2 ones, and because I don't remember how combinatoric it works, I made the math. I can actually figure out in a second how to do it. But the point is, because these 2 ones are left out, that's why we have 45 combinations. If we have only 1 left out instead of 2, we will have more combinations. And then we have to do the permutations. Why? Because in every position, I'm then doing, what I'm doing here? Oh, here. So basically, what I'm doing here, for every digit, I'm going to zip them together with the permutation. So I'm going to put all the letter S, E, and all in an array. And I have another thing that I'm going to match these numbers with one of these letters. And I keep permutating them. So I'm giving you all the 2 million possible solutions. Okay? The first one is working with a combination without the numbers, and then it's going to permutate with all these combinations. I'm talking too much, sorry. That's clear, right? More or less.
Yeah, I mean, I'm not
Sorry.
familiar.
Sure.
There's a lot of little things, like just that send state. Send
Which one?
equals,
Which one?
right there, you're pointing to it below. Send equals the string
Oh,
send.
this is cool.
Okay.
I like it.
Iterating over the characters.
Let's look this one. Let's look this one. Okay, what's coming out from this one? This map is basically character, number. Okay, it's a map with all these characters and the possible maps.
Okay.
And then we have all the possible maps for this problem. What I'm doing here, I'm mapping for every character. Okay.
That's what's converting it to an integer.
I'm going to reduce, and I'm going to do this very nice trick. I'm going to basically make the first position D, and then this number multiplied by 10, and then this number no, sorry, I'm doing the other way around. Sorry. I'm going to do this number, and then I'm going to do this number multiplied by 10 plus this number. And I'm going to do this number multiplied another 10 plus this number. This is pretty cool. It's me being fancy and trying to fit this in a slide. And I thought that was a slide just I'm going to move over very quickly. But I'm glad you asked. So this is what reduce does. Reduce basically, you have a sequence, kind of sequence of things, and I'm basically mapping this function.
So the end result is that send is an integer with all the current
Yes.
decoder.
Yes.
And then you say
So
send.
if S is 1, E is 2, N is 3, and this is 4, this will be 1,234. It's a fancy way to do it.
Okay.
Why? Because I'm mapping with the map, mapping is very big with the map, and then I'm going to do the trick to build the number. Yeah, there's a lot of information here actually.
So where's the monad here?
Yeah, in theory there is the monad. The monad is here, but it's not a monad. We're using it as a for loop. So no monad. There is a monad, but no monad.
Invisible.
It's just evaluating.
It's the invisible one.
Same thing. Install.
I'm sorry, yeah.
So monad just gets immediately evaluated. So
Say again?
monad just gets immediately evaluated.
That's a very good question. No. Until I write this, nothing get evaluated. That's a very good question.
By the send equals send map review, like by the time that executes.
Yes.
Yes.
No, that's awesome. You know why? Because sometimes, especially if you're new to Scala, I remember with the Junior developers that now are not working with us anymore, it was like magic. The fact that you write all this and nothing happened. And then you write this and
We call that hard profile.
okay?
I got another question.
Sure.
Go back to that slide. So-
But the good stuff is off your comfort zone.
Show me how to write in Heritage Scala.
So
No, I'm joking. No. All
you
the
call
all
solution.next
Yes.
once,
yes.
and that's because you yield once?
No. That's okay. Why I'm calling that? Every time there's something crazy and without any explicit type, I would look for the type. So the question is, what's the type of solution? Here. Oh, this is a for loop. Interesting. What is this? Okay. Oh, this is just an example. So a map, in this case, I think is going to pick up a list model. So a map could be seen as a list of key value pairs. Okay. So this is it's actually a sequence-like model. By the way, the point is, the thing is a list. Okay. It's inaccurate, but it's good enough. So this will be a list. Okay? But a list of what? What's the parameter of the list? It's this. It's a tuple with 3 numbers. Okay? So when you call next on a list, you get the first element of that list. Thing is, it's a kind of a pressure. It's kind of like a pipe. You know those one, do we have in mind those pipe where they put the money and they send the pressure
Oh,
Oh,
yeah, they have that in banks sometimes.
Yeah, it's the same
Yeah.
thing.
Yeah.
This guy is going to create vacuum because he wants maps. Because I'm going to create the vacuum and we get the map from here. So nice way to put it, actually. And this is why all the smoke goes through the pipes. Because of that, because you're pulling here, this guy is pulling, and this guy is pulling.
Okay.
But yes, this is a kind of a list. I think it's a sequence line, to be precise, but let's think that there's a list. Sure.
So is calling next, how is that different from calling here? Solutions that at the bottom.
This one, yes. Oh, it's the same. Actually, we could call head, yes. We could call head. I tell you what, I think this is, I said this is a sequence-like, and sequence-like has next, but not head. So in other words, if you look at map, in Scala, you have what's called sequence-like, and then you have list, and then you have, I don't know, sequence, vectors.
Okay.
In this case, I think we have map,
Okay.
capital A. So this is what I should check the exact type. So because it's map and sequence like is a model, I think the inference type is sequence like. But again, I need to check. If it's not there, it's something else between map and sequence line. That is why. And I'm pretty sure sequence line has next. I'm pretty sure.
There's no state there if I repeated that statement twice. I said solutions to the next line, I get exactly the same line. I get still the same answer.
Oh, this one.
No.
This tree.
No.
If you call next again,
If you call
I
next again,
think there's no other solutions. I think it's at least with one element.
then you would get a different one if there was another one.
Yeah.
So-
Well, that's the thing, because if you are, then you're changing some sort of state on solutions, and then it's not immutable.
Okay. So when you call state, okay, let's play this thing. When you call state, what you do, you start spawning things. No. Okay, I'm tired. Yes. Okay. This is yes. Okay, we stop here. We haven't explored the whole thing.
Oh.
But then you call next again. You do the whole tree until you get here and explodes. It's like you call next on a list that is already
So
done.
every time I call next, it's actually referring back to that code above. Doing some sort of evaluation. Didn't you?
Yeah.
It's extremely lazy.
Yeah.
Okay.
Yeah.
Okay.
Honestly, I was not expecting all these questions here, but yeah, so I just put that here just to move on.
So that send more money puzzle, similar problems might have two solutions or more.
Oh yeah. I also have a Prolog solution and a Lisp solution, but I put those in a
not
bonus slide because
limitations. I mean, there's different numbers that would
Oh, yeah.
satisfy.
that's okay. This problem has only one solution, but there are these problems. There are sometimes many solutions. Yeah.
So it would find them all.
Yes, absolutely yes.
How would you find the next one? Calling solutions.
Next again, as you said. Next again, and you keep spawning.
So we could say solutions dot to list, and it would actually have
Yeah. Yes.
calculate them all.
You will do eagerly and happily. Yes.
Okay.
Yes. Thank you.
Convert to
But I mean, it's awesome, this space. The question is, going that first, from left to right or right to left, depending on how you build the tree, is this the most interesting way to do it?
It'd be the
No, how
easiest
this
way.
is stuff.
It's easy, yeah.
Wait, this is gonna be
Like we did brute force, then we did something else. Is it the best way? Probably no. Probably yes. I don't know. All I'm saying is that there are many ways, many search techniques. And now I'm scared because there's people with PhDs in this room right now, and I'm really scared. But dynamic programming, forget about it. Where are we? Oh, I like Simulate.
Oh, yeah.
I don't know where we are right now, but
Simulated annealing solution.
this is where I want to go. There's no blockchain technology, so I'm getting an next one. Genetic algorithms. Yeah. So let's go. We're going to check this cool stuff. Let's try a genetic algorithm. How it works in this kind of problems. Right?
You have slides on this?
What's that? Yeah.
Okay.
And I also, as I said, I have references.
You have slides on all those?
Say it again?
On all
all
those
the
different
things.
No. We're going to see genetic algorithms and then we go
I
for
want to
drinks
see
and food.
simulated annealing.
We need a lot.
This is awesome. Oh my god, man. This is something coming from mechanical engineering. When you clean like metals and other things, I think somebody in the
Code it up.
I don't have
Oh,
anything
it's just
about that.
live code it.
I can do that.
Anyone have yakety sax ready?
But let's go to this one that is cooler, and I have a paper to actually back to. Okay. So if you're interested about this, check the paper. You guys are familiar a little bit with the genetic algorithm? It's not needed, but yes, it's not needed because I'm going to tell you the 3 things you need and that's it. Thing number 1, individual. Let's define an individual in this scenario as a vector of length 8. Ta-da! 45 different species. The combination, remember? These are the species. 45 different species. Okay? A species is the one that have A and B different, okay? This is the way to define a species. And then you have different individuals depending on the combination of the other numbers. Sure. Oh my god, okay.
Immature question, but is the solution space continuous for this problem?
Okay.
I mean, because a single, an iterative change in your proposed solution, I mean, is there, I'm not sure how that would, is that going to get you incrementally closer to the end?
That is correct. I was going to say that we could probably find a function as all I'm doing. Okay, let me go back. Tonight, I'm going to show a fitness function that is rubbish.
Okay.
But that's a good thing. Somebody wrote a paper about it. So I can mention, oh, they use that fitness function. It is absolutely inaccurate. It's like a very bad heuristic. So your question is very good. I could think